Good morning, folks. I woke up this morning checking Twitter, and it seems like some people are watching the videos I'm making. So here's another one. Do have to start my day with this advent calendar, though. If you're not watching this during Christmas, then you're missing out. Number five. All right, this was a gift, but I mean, it's good to have a advent calendar. It's always fun. All right. I guess let's get started wherever we stopped last time, right? I was in a speedrun move last time, so let's restart. So there's an expansion factor, right? We keep doing this ratio. Although this is between plaintext and ciphertext, so this is not ciphertext. You know, 56 megabytes, it's not big. For 2 bits, all right, that's not great. I guess this is what we know, right? Overhead. Do we really care about compression at this point? It's interesting that they're doing compression of ciphertext, but we don't even understand much of how the other stuff works. So intermediate ciphertext compression. So client does it, server does it. Server does it. All right. I mean, it would make sense, right? That GLW is N. Right, K and why is LW N plus 1 then? I guess N is the bit size of a node log to Q. Right, do we have N of them? LW was just because there's like that's the size of the key, right? And then you're doing that times 2 probably because you have the mask. It's just weird that the N disappears in a GLW because you would expect for the size of a key you have K of them, and the K of them are of degree N, so it's almost like there's a little N missing here, but it makes sense, right? It makes sense, sort of makes sense. All right. I don't really care about that, but I'm just gonna go through it so that we know that it exists. I'm more interested in bootstrapping in general. Or you know what? We should follow what's interesting to us. Let's read a bit of that to see what's going on here. At least we know we can compress ciphertext now. Yeah, I mean, it's the same as ZK. If it doesn't fit into one unit, whatever is the field element or something like that, then you just decompose it, right? You have like limbs, would be the programmer's term. Blocks, limbs, you know. The thing that's weird to me is that in TFHE, my understanding is we're dealing with bits, and so why do we even care about limbs, different limbs? Is if a ciphertext is but they said here that a ciphertext can be 2 bits. I guess I'm wondering why a ciphertext can be 2 bits. We should try and answer that at some point. Let's just ask. We haven't used AI so far, right? Why is a ciphertext 2 bits? I thought a ciphertext only 1. Yeah, we gotta start using our friend Chat GPT. I'm sorry I had to wait for the 3rd episode to do this. There's Boolean TFHE. All right, the body is in that ring, right? Is modulo Q, so why would it only be a bit? All right, the body is 1 integer mod Q. I mean, we don't care about the body, but it's the size of the message, right? Because it's the message plus the inner product of the mask times the secret, blah, blah. By the way, I just woke up. This is my morning coffee from La Colombe. Cold brew always hits good, but before I get my cold brew, doing a speed run is extremely difficult. So all right, let's get focused. Is that module so small so you can have a huge carry maybe? Is it or is it not? Oh, maybe 2 bits because of the carry? It's 1 bit, but it can become 2 bits because of the carry. Maybe. I don't know. All right, that wasn't super helpful. Yeah, homomorphic analogy to the standard multi-precision arithmetic. So you have a bunch of limbs, and you're doing your arithmetic like you do your arithmetic in the clear. That makes sense to me. That's exactly what we do in ZK, by the way. I mean, that's not true. In ZK, there's because you can use hints, you can sort of compute the result of the big hints, because we're looking at big hints here. You can sort of compute the result of the computation and then pretend the limbs are the coefficient of a polynomial and write a polynomial identity and try to prove that you have your thing, and that they can actually be faster for reasons. Yeah, 2 bits. Again, the limbs are 2 bits. So here we have a normal, base decomposition, not like last time what I was looking at. Maybe we should have asked Chat GPT what was going on there. Mm. Mm. Shouldn't there be a sum? Oh no, okay. Interesting. Oh, okay, so it is a weird encoding again. I mean, called Radix Encoding, like it's something basic. And whenever I read these kind of things, I feel dumb. I'm like, all right, this sounds like something I should have learned in school. Maybe I did. The Radix Encoding section. Carry message aware. So it's a weird. I mean, I guess it's it's an encoding, so it must be injective. You can decode it, and you'll get the same stuff back. But it's non-standard. Do they have an example? So we use beta equals 4 for all I. Yeah, so you have 4 times 4 times 4 with that product. I mean, it's kind of weird because here we use the same beta I, so it just looks like a normal, a basic composition. But if you don't use the same beta I everywhere, what is this? Why do we have these at the right. That's a weird way to write that sum. But the last element is all the multiplications without the last without the last element, I guess. I'm still very confused about all this padding stuff that we read in an earlier video. So that's the function we just created, or? What is that PI here? It's the message times the carry. What is that? What is that? Okay. What is the carry message paradigm? What section is it defined in? So I guess at some point we have to understand this kind of representation where you have the error, the message has been shifted to avoid the error using that ratio. I believe that we looked at, and then there's this like padding that is here for the carry. Maybe I'm not sure actually. Oh no, needed for the PBS. So it's really not for the carry. The carry shouldn't reach that place. Because apparently we need one more bit for the PBS, for the programmable bootstrap. Maybe that's the base, you know, and this is for the carry. How big is the carry? Is it like every operation that we do, we need a carry? That's what it sounds like almost. So I mean, so the carry can only absorb one operation, and then we need a bootstrapping. Let's ask, right? See that the padding is big enough to padding the carry, or is that the carry space is big enough to absorb to allow just one operation, and so we have to do bootstrap after every operation. Ugh. For additions, maybe for additions, right? But how about multiplication? Degree of fullness. I wish there were the numbers here. All right, so no, the response is no, but we didn't learn much. Okay, let's go to section 2.3.1. All right, we got one piece. All right, I remember that now. So padding bits here needs to be 0 for PBS, right? After performing linear operations. How about multiplications? Yeah, I mean that should, if you don't understand carry, this gives it to you, right? Wait. Where is the message to? Should a message be 1 just to carry 1 bit? See, I should have done that earlier. Oh, that's the modulus, right? So if you want it to be 0, 1, we have to set it to 2. All right. See, this is so useful. This is how I read papers now. And sometimes it's wrong, but you can either, that's where you add probabilistic feedback to your setting. Right? If you know the video from Veritasium on how to become an expert, they say there's like 4 rules. I don't remember exactly what they are, but like one of them is to have a valid environment, like to have a feedback loop, and then to have a valid environment. And when you play poker, for example, there's so much chance that sometimes you think you play a good hand and then you get punished for that. And so that's not good feedback. You didn't learn anything. You might have learned something wrong. You think your good hand actually is worthless because you lost. So you need a valid environment. A compiler is a great environment. Whenever you write code, the compiler will tell you if it works or not. It will tell you, it will run it, gives you exactly the correct values at runtime. You know what I'm saying. Perfect environment. Using Chat GPT to read papers, I don't know if it decreases the luck, or you might learn something wrong. But at the same time, if you read something without being able to ask about it, you might actually think you understood something, but you didn't understand it. And so you just, you don't really have that feedback. Whereas here, at least you can like push something, it tells you, no, that's not like that. And if it's correct most of the time, like, I don't know, let's say if it's correct 100% of the time, then it would be amazing. This is much better, right? If it's correct 50% of the time, it's probably as good as poker. But I don't know, this is probably correct 80, 90% of the time, especially for small questions like that. So this is very useful. Anyway, I'm getting distracted again. I mean, I gotta make a YouTube video out of this as well. So I gotta say some stuff. But at the same time, we're supposed to speedrun this thing. So let's get back into reading. All right, so we got that. I don't need to read the rest. So the message space is P. You know what it is? I don't know. The ciphertext slot has capacity P. That's the modulus. I don't get that part though. It shouldn't be like message plus carry, you know? Even carry P over 2, that doesn't make sense to me. So this is one thing where I'm like, yeah, is it correct? At least it says 2 3 through 2 3 1, right? Y carry times message equal P. And what is the beginning here? I hate going back to previous sections, but when you don't understand something, you sort of have to do it, right? All right, the encoding is when you're just shifting the message, right? That's what we... Oh wait, P is the message modulus. That's why I keep. But if P is the message modulus, then what is message here, right? So Q is the actual modulus. You saw that, right? The final modular reduction will only change Q to 0. Can only occur when pi equals 0. I'm right. So let's take a step back, right? So we are encoding values, and here we're trying to figure out like what are these values, what can be encrypted, and the size of what can be encrypted, and there's a plain text space that needs to be big enough for a message and a carry, or vice versa, right? No, I think this is it. So plain text space needs to be big enough for message and carry. I still don't understand why it's a multiplication. Didn't I ask here? I did ask, right? So it is correct. It actually is telling me stuff that I'm reading here. P is the message modulus. No, P is the plain text modulus, no? Oh my god. Right. Sorry. Plain text modulus is this. Right. But here this P is the plain text modulus, isn't it? That's what, so it's not me, right? Like here P is the message modulus, but here P is created from the carry of the message. So redefines P. Yeah. So I mean, Chat GPT got it as well. Or maybe the message modulus itself has enough room for the carry, right? Because that padding here was for the bootstrapping. I think that's what's confusing me. I thought the padding here was the same as the padding for the carry. Oh my god. Is it the lack of coffee, or maybe it's not just me? I don't know. All right, so they say the padding here obviously is for the PBS operation. So that's what I keep confusing. There's the plain text. This is the entire plain text. It needs this padding for the PBS, the programmable bootstrap, or the bootstrap. And here is really the what do they call it? The message modulus. And and this message modulus really is an actual message modulus and a carry modulus. And I still don't understand why it's a multiplication. We can ask here, why is it a multiplication? Why is it not carry plus message? Obviously, no, I know, because we're not talking about like surface area. So it's not going to be an addition. But like I'm having trouble making sense of it, if that makes sense. But if you look at a diagram like this, right? Like you get 3 bits. If you push it here, you multiply by 2. You push it here, multiply by 2. You push it here, multiply by 2. So you have to multiply by 2 to the 3. And so to take the entire volume, you do have to multiply it by the size of the carry. So I think I just convinced myself that this makes sense. Hopefully that was convincing. But yeah, carry times message equals P. I mean, in this example, it's really clear. Woo! All right, victory lap. Also, so let's go back to that one then. Small steps, baby steps, but it forces us to think about these things. It becomes easier to think about these things. People who understand these kind of these FHE papers have spent so much time reading them. So we have to be slow so that we can be fast. I don't understand why we take these values that we used to have. Like I don't get it. I understand why carry times message bool. I think that's what they should have written, right? Carry bool times message bool has the same relation as message times carry. And it has to equals to P. Right? Why P over 2? What the fuck? Isn't carry bool times message bool equals message times carry equals P? Why is it P over 2 now? Oh. So in 2.312, why is it? And I'm fucking with the context window here. I'm going to have to restart it at some point. That's annoying, but why is 2.312? Where is it? Not carry. Oh, of course. If we had a message on that side, then it would be P, right? But since we divided by this message, which is 2, we divide P by 2. Yeah. All right. Wake up, David. So we do have carry bool times message bool equals P. And so carry bool equals P over message bool, which is P over 2. All right. So the carry is going to be and so yeah, I don't know how much we're going to choose here, but that makes sense. All right. Let's move on. I don't understand why the functions themselves can be chosen to be negacyclic. Let's ask, like it's time we dig a bit into these terms. So I was right about these negacyclic, I don't know how to say that, negacyclic polynomials, but they are negacyclic lookup table. And that's something we haven't touched at all, right? Ooh. Polynomial convolution. What is polynomial convolution? Sometimes, it's good to end up in this rabbit hole because you can't always get answers and be confused. So you have to go in this rabbit hole so that next time you get these kind of answers, you're not confused anymore. And actually, I'm sure I've learned about that and I forgot. So the more I revisit it, the more I'm going to remember it. But I do have to, take a conscious decision on like what I'm double clicking on. Anyway, so convolution is just an algorithm. Okay. I think convol is because there's some weird stuff happening when you're in these polynomial rings. Oh, I hate it when they ask me for this. Yeah, that's interesting. So there's a weird formula that tells you stuff. Anyway, I'm not gonna learn about that today. What was I even trying to learn? Let's go back to this. Lookup table encoded as polynomial. We know that in ZK. I'm wondering if it's similar to this. We looked at the blind rotation. I already forgot. Or is that when we're just multiplying? Rotates a polynomial negacyclically. So that's the thing. Depending on the modular, doesn't make sense in this example because we're sorry. It doesn't make sense in this example because here we're in a we're not in a quotient like a polynomial quotient ring. We're in a polynomial ring, I guess, or like a normal polynomial ring. But when it's quotiented, then you have to do a modular reduction, and so you get these weird formulas. I think that's what I understand. And I think the weird formulas is because maybe because I'm not sure actually. I don't know. This is interesting. I feel like maybe we should revisit that because it doesn't really make sense to me now, and I don't think we should stop here. But this is interesting. I'm not sure why that would be the case. Yeah. Because for every square, no. Oh, yeah. So imagine you're squaring this thing. You're going to get x squared q over 2 square, q over 4, q squared over 4, and then 2xq. Oh, sorry. 2 times x times q over 2. So xq, which is going to be 0. And so every square is going to have like something special. And so when you negate things, that's how far I'm going to go here. Or am I? All right, if your function is like, c0x plus c1x squared plus, I mean, let's try that. Then plus c1, right? So it's you need a minus here to be able to say that it's minus f of x. But if this thing here gets us to q over 2, q over 2 is minus 1, by the way, right? No, that's not true. What am I saying? And q minus 1 is minus 1. So what are we doing here? Oh, right, okay. And let's just write it out. I mean, it's gonna be because of the modular reduction, right? I don't care about the lookup table though. So the xq terms vanish mod q, that I noticed earlier. Okay, so the annoying thing is that sometimes the LaTeX drops also. Come back. Oh. All right, I'm sorry. Let's I think I'm overthinking this one. It's probably these kind of things that are going to be become clear in retrospect. Especially, I don't want to read too much from Chat GPT. So all of that because we went into that rabbit hole. Is there some part in the paper, what section, that explains the Negacyclic stuff? Maybe that's going to be better. Degree of fullness, I guess that's the thing that tells us, okay, we went too far. Let's read that section and then let's go back to that. All right, P is message times carry. What is mu? What is micro? All right, okay, so that's something that we keep track of. All right, this is where we think the message is. And when we think the message has reached the carry, right? Right? So message is the modulus, right? So maybe it's 2. So we're gonna pretend it's initially the message is 1 because we don't know if it's 0 or 1. So we're gonna assume worst case. So it's the upper bound. All right. Yeah. Just reminds me in ZK when we do big integer operations and we want to avoid doing modular reductions all the time, we sort of track the size, and once it reaches a place where doing one more operation might, due to estimated bounds on the value that's been operated on, we know that if it reached the maximum value that we estimated accurately, it would break, it'd wrap around, it would do something weird, we would lose the results, and so we know when to do a modular reduction. So this is a technique that was in XJ Snark, I think. You want to check XJ Snark, the paper. By the way, as usual, if you understood something I didn't understand, please write it in the comments. I'll check back the comments and I'll just read it. This is interesting. So you have to sort of monitor both things, right? The noise and the carry, which sucks. But they choose parameters so that you only have to monitor one, which is the carry, and the noise you know will always be under. Okay, that's sure. So the bootstrapping does a modular reduction to remove the carry and removes the noise at the same time. That's really interesting, right? They have two concepts of noise in a way. I mean, the carry is not noise. It's supposed to be accurate, but it's something you want to get rid of. Okay. Okay. And this we looked at last time. Adding, rotating was just multiplying with this. I'm guessing they call it rotating because of the Negacyclic stuff that we saw earlier. Because we're in these polynomials modular x to the n plus 1. That's this thing. But yeah, I don't know. Maybe we can read more about that, right? So that was my question here. Section 2.7. Ooh, all right. Remark 24. That's why we're going to have to read, right? They don't say much about it. Is there something else that we can read before we get to that section? Obviously, that section is probably the most interesting section of this entire thing. So I should reach it, if not in this video, in the next video. Maybe we should read more stuff before reaching this. But that's gonna be the cake, right? The icing on the cake. This is, even though it might take a few reads, that's gonna be the interesting one. Okay, so let me read these, and maybe I'll find some other stuff I can read, and I'll keep that for the next video. Let's see, or maybe I'll do that now. Let's see. Let's see what this says. It's the only place where they're formally defined. All right. I believe you. I believe you. They don't even define it, do they? They say that there's this property, but and by the way, this is P, not P over 2 for some reason. Oh, but because we're in Z2P. But they don't say that this property means that it's negacyclic. So I believe you, though. It's so interesting. Works without padding. I guess we should try and understand PBS and see where it breaks basically without the padding. And the symmetry equation is interesting. Whatever. Oh, give me an example. We should at least see an example of a tiny negacyclic function, please. Examples are the best. And Chat GPT they used to be very bad at giving examples. Every time I would ask for examples involving matrices and stuff like that, it would always give false, completely wrong examples. I think he got much better with like all these reasoning tokens and it's not, if we are not gonna get the LaTeX, it's not gonna work. Uh, Unfortunately, it just has so many LaTeX issues. Like I have LaTeX issues all the time. We'll see. What was blind rotate? Let's go. So let's ignore that for now, and let's kind of revisit stuff that we've seen before, just to solidify things. Blind rotation. I'm trying to remember. I don't remember. All right. So you have two message and returns it's kind of weird, right? So it's not a multiplication, it's a rotation. That's how they define rotation, right? You multiply it by x, but the x is parameterized by the second message. So I don't know why that's useful. I don't know why you would want to do that in a circuit. I guess they say it's a main building block of the PBS. So we don't know how to do that yet. Oh, they explain it here, so we can look at that. Actually, that's gonna be good because it's gonna remind us of all this GLW. So GLW is it's the easy one, right? It's the first type of ciphertext. We're in a polynomial quotient ring, a vector of polynomial quotient ring elements, right? I can show it to you here. We have our message here. Our message is always one element. Why am I saying vector then? What is RWE? Wait, where is RWE defined? No, I remember. Uh, so it's when you only have the size of A is one, and maybe that's something I didn't really understand, right? So I thought the message was kind of impacted, but the message is not impacted. The message is always one element of the ring in LWE. Message is where is message defined? M here is in this ring, or in the polynomial quotient ring, M is in this R, which is this polynomial quotient ring. But it's never anything else. The only thing that changes between RLWE and GLWE is the size of the mask and the size of the key. Right? I think that's the only thing. And that's what I misunderstood. Let's ask. The only thing that changes between is the size of the key. Right. Not quite. Yeah, this small change has consequences. I understand, but I just wanted yeah, we don't care. Right? That's the only thing I wanted. By the way, oh, it's nice that it repeats the same message so that give me a tiny example of a Negacyclic function. Let's try again. And it's nice that it repeats the message. I hate that bug in the new Chat GPT desktop, but here it's great because it re-uploads the PDF. So that's great. Let's see if that times it works. All right. So where was I in this? As blind rotate, right? So the message is just this it's in this thing, polynomial quotient ring. We multiply with this. Constant term of m is dm plus c mod nth coefficient of m up to sine. What? We rotate one ciphertext by the negative phase of another. That's a negative phase. I don't understand these terms. And we know that the constant term of... I don't know how we know that. I assume if you write it down, then it makes sense. But, you know. Oh, yeah. No, I don't know. Okay, let's look at what he wrote there. Yeah. Just doesn't work. All right, what's a redundant lookup table? Why is it redundant? They don't really explain, right? Why it's useful. In ZK, you have to be redundant because of stuff, depending on the scheme you're creating. I'm wondering if they have the same problem here. But okay. So you have secret keys of different shape because we're looking at LWE, GLWE, message of, okay, this is a message, but the coefficients are just representing a lookup table, right? And what's interesting is like the entries of a lookup table. So it's a lookup table is one dimension, right? One column. You don't have to think of a lookup table as like, you know, XOR lookup table or something like that with 3 columns. Like here we only have 1 column. We have different entries. We just pretend all of these entries are coefficients. And some of the entries are repeated, I guess, R times. And M is the redundant LUT, right? And it's here, right? So the CT is the lookup table. Interesting, there's a CMOX. So we start right away, right? We just multiply it with... And what does that even mean? So you multiply all, that's a vector with the mask, the secret, and everything. So you multiply everything. And that's similar to the... we did, was it in simple operation? Or it was just rotation, right? Although that's how we did the external product. So module switch maybe. Oh, I'm looking at that. Oh no, that was not the external product. That was... oh my god, I can't remember what we read. Yeah, it was in linear operation, right? It was the rotate. That was the one. So you multiply this x to the power omega to everything. They could have just written like we just wrote, right? X omega times ct, right? They could have just written that. But this was the rotation. You're just multiplying with this x omega, and it just works. It gives you the output is the encryption of m times x omega. And just multiplying by x omega just works. Right. So this is what we're looking at, right, here. This is the exact same operation, except it's minus b. Oh, and is it an accumulator again? CDR. It's an accumulator where we either... Wait, what is the condition thing here? This is the condition, right? So what is CT? Wait, what is this thing here? Bootstrapping key. So the bootstrapping key tells us if we just keep the accumulator, right? Nothing changed, or if we multiply it with x to the power of the mask. And I guess it just works if you input if you write it down, maybe, but I'm still... Let's understand the CTI here. A bootstrapping key from S to S. What does that mean? A bootstrapping key from S to S. Do we see that before? It's a key that helps you to go from... Also, this is the other thing, right? Bootstrapping gets you from one type of ciphertext to another. So maybe that's... Yeah. Let's my next question will be like, what does it mean, a bootstrapping key from S to S? Is it because we're switching ciphertext type when doing a bootstrap, or do we define this for the first time? All right, so let's finish reading this thing, because it's a piece of the puzzle. Even if we don't understand it, it's fine. We'll finish reading it. Then we're going to look at the example and ask the question, or maybe ask the question and then look at the example. So this motherfucker... I don't even know how to read these. Are we still in the definition 13? We use the term megasolve for each block of successive redundant values in an R redundant lookup table. And is this MF still part of that definition? It's not clear, but it probably is. X to the power minus R over 2. Let's read it, right? A sum from 0 to n over R minus n over R minus 1. So n over R of these guys. I don't know why we have a sum here. XI R. So it's going to be, so it's going to dump to start at 0, right? XR, X2R, X3R, X4R. And Fi is the lookup table, right? So f of 0 equals the first entry of the lookup table, f of 1 equals the second entry of the lookup table, and so on. I don't know why here it has a tilde. Oh, an encoding of a message Fi. What's megacell again? We use the term megacell for each block of successive redundant values in an R redundant lookup table. Right here. So okay. So I understand. We have the degree of f is the degree of f is n minus 1 maybe, or n whatever. And so you have n or n minus 1 entries in your lookup table, right? But you actually you don't have that many. You don't need that many maybe. And so you're gonna repeat r times the first entry, and then r times the second entry, and then r times the third entry. So you're dividing your space into blocks of size r. And so n divided by r gives you the number of values in your lookup table. And so this thing here gives you all of the different values in your lookup table. So I guess here it's going to be f0 and then fr and then f2r up until that value, and it gives you the distinct value between each block of repetition, if that makes sense. Right? f0, f1, f2, f3 up until fr minus 1 is the same value. So here, I mean, this you don't really see it, but the next value here is going to be fr minus 1. So you don't need to repeat all of these entries that are meaningless. Times xj. So here you're repeating the, right? Fi. Oh shit, we're still in that sum. All right. So I guess you're sort of flattening. You have this. This is a a polynomial, and you're trying to figure out where your Fi are. Like, for example, f0 is gonna be I is gonna be 0. So this is 1. J is gonna be we're gonna repeat it. So we're gonna have 1 x squared until x r minus 1. So this is how we interpolate almost like this lookup table. I don't know why we have this here, but at least I understand this part. This is the polynomial where we interpolate our lookup table. And for the second, r minus 1 value, I think this is just maybe a shift or something like that. I'm not. It doesn't seem to matter. I mean, of course, it matters to some extent, but I'm still trying to understand this. So we'll have f0. It's still there, right? But we don't care. That's what I was trying to explain. And then all of that is going to be times 1, you know? And then we have the next guy here is going to be x times r. So that's the next block is going to be for f1. Right? And so you're flattening this thing. This is your first chunk. This is your second chunk that's shifted by x to the r. And so the first r coefficients are for the first value in your lookup table. That's repeated r time, right? The second r coefficients are for the second value in your lookup table. That's repeated r time. So here I was wrong, wasn't it? Wasn't I? F1 is coming here, and it's going to be different from F0. Right, so we're repeating r times the entry fi. So I thought f was something where it was already repeated. Actually, no, it's the motherfucker here that's repeating stuff. And this x minus r over 2, I don't know why we have it. And depending on the control bits, which are from the bootstrapping key, which I guess is either 0 or 1, encryption of 0, 1. And we have many ciphertexts, right? There's many of these ciphertexts for the length of n of them. We're doing this operation. So it's this blind rotate. This is really annoying. It's like to really understand these things, it's like you have to take an example and understand why this works. And maybe we can ask Chat GPT to write these examples for us. But usually it's pretty good to write that ourselves. So anyway, I think we've seen enough of that. Let's keep reading. Maybe they will have an example. I would love for them to have an example. I would love to run some Sage math that runs these examples. But anyway, let's focus. That's interesting. I don't understand it, but this will probably become relevant later. I mean, this will become relevant later. Yeah, that's algorithm 18. So they have to be binary because these are control bits, right? No, I'm mistaken. We're not talking about the same stuff here. No, we are talking about these are the control bits. It's the smallest. Right? Yeah, the encryption, the motherfucker at the end. That is the redundant LUT, right? So it's, I guess we have this theorem every time that tells us like the noise, right? Because we have to keep that in check. So we need these theorems. This is really annoying to have, I guess. These are such complex systems. Not only they're hard to understand, but also you have to make sure that the noise never. You need these equations for understanding how the noise changes. Wait, what is CTF again? All right, CTF, encryption of that. A trivial encryption. How is that possible? Do you know why it's possible? Oh, because it's part of the input. So we already know what we want that lookup table to be, I guess. We saw trivial encryption, right? It's with a mask of 0 and error of 0, I guess, because we don't care about someone being able to decrypt. Right. Error 0. This is so annoying. There's so many different components that you need to. We're in 2n here. And these are detail, right? Like these are usually you don't even pay attention to that. And you're like, yeah, these algorithms work. And then once you try to implement them in practice, this is why this document is amazing in many different ways, because they had to implement this thing and then they run into all these implementation detail issues, like the modulus needs to match, whatever. And that's when you have to think about these problems. And it's amazing that they wrote down, in a very clear way, all of the stuff that they needed to know in order to implement these things. So this is amazing work. You don't see everyone doing this kind of work when implementing something. And I guess what they implemented was very complicated, so you need this kind of rigor. You need to be rigorous when you do these kind of things, and that doesn't mean there's no bugs, right? It's so complex that I would assume it's error prone to implement something like that. But the nice thing is that if it works, if you implement all of that and it works, then it must be that your equation were right at some point. So that's very reassuring. I cannot imagine what it must have been to implement something like that and debugging it. And if something doesn't work, like figuring out why something doesn't work and at which part of the stack doesn't work. Of course, you can test these kind of algorithms independently and see if they work. And so if algorithms work independently, then the whole thing should work. All right. So this blinding thing, this blind rotate was harder than I thought. But at the end of the day, we have a ciphertext and we want to multiply it with the power of x, but we don't know what that power is, right? And interesting, the noise is also in that power, which is fucked up. But you carry that noise with all of your equations. And why it works? Not super clear to me, but we multiply with the body and then we have to cancel whatever we multiplied. The body has a sum of the secret keys and the mask. When the secret key is 0, you don't need to cancel anything. So that's why we have the CMUX. When it's 1, you have to cancel it with AI. It intuitively makes a lot of sense. I'm sure if we put the equations on paper, it would make sense. All right, we're done with that. I don't want to start with the PBS. Let's look at these examples. And let me ask that question also, just so we get an idea. But the Negacyclic, and then I'll stop the video. I think we spent a lot of time together. This is too much time. I'm not comfortable spending so much time with you. Just kidding. But I mean, this is a lot, so a break will be warranted. Yeah, what is big S here? Where is it used? Is the encryption? Oh, that's so funny. Right? You need an encryption of that key under another key. I guess it's like key switching, maybe, or I don't know. Given input binary, blah blah blah. Yeah, they don't explain. Is it because bootstrapping switches ciphertext types? Yes. Oh yeah, that's sort of the intuition, right, of bootstrapping. I guess I never mentioned that. It might be mentioned at the very beginning. I mentioned it in my book. Every time I try to remember something, I just go back to to the book. I don't know if you can see. Maybe I'll I'll put myself in full screen. So this is the book. And I'm not. This is not a plug. This is actually what I'm doing when I need to remember something simple. I have chapter 15 has a part on FHE, and I explain some very basic stuff. And I don't know if I'm supposed to do that with copyright and stuff like that. But if you look at that diagram, you can see that there's a message. We're encrypting it with a public key. Becomes a ciphertext. Oh shit! This is not what. This is just a homomorphic evaluation. We're looking at bootstrapping, right? Okay, here's the bootstrapping. Let me try to make it clear. All right, so the new cipher is getting too noisy. See on the very left. So you encrypt it with another public key. You get a ciphertext of a ciphertext. So you have a clean ciphertext, but what it encrypts is a noisy ciphertext. And what you do in this homomorphic function that you do, you decrypt what's inside. By decrypting it, you just get a ciphertext with acceptable noise. And when you decrypt it, you need to decrypt it with a key, and that key is encrypted as well. Otherwise, what's the point, right? And then you get a new ciphertext, but in the different encrypted with a different key. So maybe we'll have to key switch to go back to the first key. I don't know. And that's the rotation with like a secret. Maybe is the thing to decrypt inside our circuits, or it's maybe the thing to encrypt in the first place. Or actually, encrypting should be easier because it's a public key encryption scheme. We haven't really seen that. I guess there was a section on public key and how to create a public key FHE stuff, but we didn't really see that. Maybe we should go back to that. Maybe at some point we should just read the overview. Wait, not this one. There's like an intro. Oh yeah, maybe at some point we should read the intro. Although it doesn't seem very interesting. Is there like a high level overview of bootstrapping? And no, it straight into the ciphertext. So next time let's look at that. Okay, and for now, should we look at that quickly? Negacyclic. The context switching is hard, but we're doing hard things. I don't understand why it's equivalent to that. After shifting encodings. Input plus P over 2 behave the same as minus inputs. Okay. So if you add this to itself, it's going to give you 2 inputs plus B. Doesn't give you 0, right? I'm not sure. Yeah, what the heck? Okay, tiny example. This is not going to be helpful because it doesn't really give us any structure. It's just like, sure, it works because of the values you give me, but all right, this is not great. Maybe that's more interesting. A Negacyclic function, because remember we're doing this. Where was it? Where was it? We're doing this thing, right? We're wondering why. A Negacyclic function is one where the second half of the table is the negative of the first half. So that's the interesting part, maybe. No, I don't know. Why is tilde m first term x in equation Okay, next video is going to be exciting. PBS. It's going to be tough, but you know. So we're going to do, my understanding is that at some point we're going to do rotations, like we're going to basically move things so that the constant term becomes something else, and then we're going to use some operations to extract the constant term. I think we saw that in another video, in a previous video. But it's these kind of weird things where we're so limited in what we can do that the way we do things is just that we rotate coefficients and we extract the constant term, because extracting the constant term is easier for some reason. At some point we're gonna have to play with like these rotations and extracting the constant term, but maybe for now we can just accept that this is a Are we doing all of these to rotate coefficients and extract the constant? Let's just see if you can tell me yes or no. All right, the intuitions are somewhat right, according to Chat GPT. And constant term are LWE ciphertext, I guess, right? That's sort of why you get into like bigger ciphertext that can encapsulate smaller ciphertext. All right. So we'll see that next time, right? Like this gives you a kind of a spoiler or like some teaser, and then next time we'll look at this. So yeah, let me know if these videos are useful to you guys, and if you want me to do more of these. Honestly, I wouldn't have made this one if I didn't receive the encouragement in the on Twitter. I think I woke up this morning with like 200 likes on Twitter or something like that. And so this is cool, you know. Like I'm not doing this alone. This is motivating in itself. And yeah. Let me know if this is useful, and I'll see you in the next video if that's useful.